Hi, this is Jahid Hassan, a UMBC PhD student in MPSC Laboratory IS department. Welcome everyone. In this talk, we present our paper titled RhythmEdge, Enabling Contactless Heart Rate Estimation on the Edge. This work has been collaborated with Imonde, Srinivasan Ramaswamy Ramamurthy, Dr. Nirmala Roy, Dr. Archan Mishra. The research work has been supported by NSF Career Grant and US Army Grant. Here is the overview of this talk. Heart rate denotes the number of heartbeats per minute. It's an important biomarker that can provide early prediction to numerous health conditions and is recommended to monitor regularly. Heart rate is monitored by ECG in clinical setup using the special skin contact lead electrode. In daily basis, heart rate is usually monitored by photoplethysmography or PPG, which is a non-invasive optical method that measures the skin reflectivity variation due to heart activity induced volumetric blood variation in peripheral skin tissues. Wearables PPG signal are predominantly used in monitoring regular heart rate. However, it requires close skin contact and specialized optical sensors. Alternatively, remote PPG, also known as RPPG system, can measure PPG, hence heart rate, using videos of exposed skin captured by regular camera sensors. RPPG provides an ubiquitous heart rate monitoring application perspective as it uses off-the-shelf camera sensors and easily applicable in practical cases. Further, it requires no skin contact between subject sensor and it provides enhanced safety for the users. Then, why are we not frequently using RPPG at heart rate monitoring system yet? Firstly, RPPG requires a robust model to estimate PPG from video due to the noisy nature of the data. Secondly, the extensive video processing and computation bars the inference using limited resource computation. And finally, RPPG had not been explored in edge devices till now for ubiquitous application. Based on the research gap, we aim to develop a low-cost, computational, ubiquitous, reliable, and stable RPPG system for monitoring heart rate continually using off-the-shelf video cameras. Particularly, we aim to build computational efficient RPPG model inference model that is supported by a range of edge devices and sensors and perform consistently under realistic videos. In this research task, we address and solve both algorithmic and system level challenges to develop such RPPG system. The algorithm challenges cover developing edge executable efficient data-driven RPPG model, facilitating video processing and PPG inference inside edge. And this system level challenges looks into existence of PPG in the video, pre-processing, computationally heavy method, camera device integration, system benchmarking for feasibility studies. In this research, we push toward ubiquitous heart rate monitoring system via RPPG by firstly proposing a pruned and quantization based RPPG domain specific model compression technique that balances between accuracy and efficiency. Secondly, we develop and prototype a edge device based RPPG approximation called RhythmEdge, and finally we benchmark the RhythmEdge for accuracy, system time complexity, memory and power consumption. Our RhythmEdge system requires stable phase focused HD videos cameras capturing subject facial skin at 30 fps under ambient lighting conditions. The edge device receives the captured video either via already integrated camera sensors in real time or cloud based communication for offline video RPPG inference. The edge device performs necessary video processing and apply the compressed efficient RPPG model for inference. It also approximates the heart rate from the PPG. Further, the system also stores the longitudinal heart rate information and notify the users. We prototype RhythmEdge for developing by developing compressed RPPG model using server resources and pipeline strengthening the RPPG system component in the edge devices. Using the server, we develop baseline RPPG model following the CAMSense architecture design. The CAMSense architecture contains CNN backbone. This is responsible for extracting facial RPPG videos from facial videos, fully connected layers on top of it to reconstruct the target PPG sensor signal. In that architecture of that FC layer and CNN layer have compatible number of parameters. We hypothesize that by reducing only FC layer pruning weight by pruning, we can reduce the model complexity significantly while maintaining the inference performance. Moreover, since PPG is a slow-moving signal, the model doesn't require to be highly precision. We propose to prune FC layer while maintaining CNN nodes for RPPG domain and validate our approach by experimenting with 3 different public datasets. We quantize and prune the model to reduce the inference computational complexity even more. The experiment with both 16 and 32-bit quantization in the RPPG context. Finally, we prepare edge executable TensorFlow TF-Lite model for edge inference. We provide 4 types of compressed model for compression between them as detailed in our paper. In this experiment, we find pruned quantized 16-bit model works the best by balancing accuracy and source efficiency. We prototype our RPPG system RhythmEdge by implementing and executing the operation required to infer RPPG system limited resource edge devices. Firstly, the edge device receives the video via word connection or web-based platform. The video processing tools of the edge devices center crops and resize each of the video frames. It takes consecutive 40 frames as a single instance and utilizes TensorFlow Live runtime execution setup to apply compressed model to estimate PPG from the videos and perform frequency domain analysis to approximate corresponding heart rate from estimated PPG signal. Finally, the edge device transmits the result to server to facilitate user communication and longitudinal health data storage. We have validated our compression method using 3 of the largest publicly available dataset, namely the MPSC RPPG dataset, MARL and UBFC RPPG dataset. The MPSC RPPG dataset contains RGB videos from DSLR action cameras, web cameras and corresponding target reached PPG signal. The videos varies in resolution, camera sensor properties, lighting, distance and containing both natural and artificial light. The MARL RPPG contains 2 videos modalities and finger PPG. The UBFC RPPG dataset also varies in frame per second. We demonstrate the compatibility of RhythmEdge by prototyping it on Jetson Nano, Google Coral Dev Board and Raspberry Pi. The 3 edge devices differ in hardware architecture and are mostly commonly used devices in our regular day cases. We provide the software stack and GitHub page. We also request everyone to check our demo paper for further detail. In summary, our prototype captures the videos and apply compressed model to infer RPPG while monitoring sister parameter. Here we see the RhythmEdge in action. We evaluate our compression technique performance by computing accuracy and comparing them against baseline and ground truth target. We benchmark the system performance for stability and feasibility by measuring the execution time, allocated memory and power usage during execution of the RPPG system component like video processing and inference. Here we visualize sample training output of compressed model and compare them with the ground truth. The Q32 and PQ32 denotes the quantized only model and pruned quantized model. By incorporating pruning compression, we can see that the increment in high frequency component while maintaining the trends of the target ground truth signal. We quantify the compressed model's performance by the statistical similarities between the target and estimated signal. We observe that the baseline model demonstrates high similarities, whereas the compressed model similarity reduces, but still it maintains a high degree of correlation with the ground truth. We measure the system lag and check for system clock by measuring execution time to perform video processing and inference. The execution time depends on specific components and considered edge devices. We observe that OpenCV processing time dominates as it performs serial processing on consecutive HD frames. The Jetson is the fastest of all devices as it has higher RAM capacity. We compare the system memory to check system stability and feasibility. We measure both average and maximum memory. Similar to earlier, the memory also depends on the edge architecture and RPPG component. We observe that this time Jetson requires a bit higher memory than other two. As per expectation, the inference stage requires higher memory than video processing. Further, the increasing compression, we can reduce the memory utilization during inference stage by a factor of 2. We also report the power profiling of our devices in the paper. We test system stability and performance under camera parameters variation like resolution and FPS. With increasing FPS, the OpenCV processing increases tremendously because of its serialized frame operation. It follows similar time and memory profile as discussed earlier. However, Google Coral Dev Board fails at 120 frames per second video due to the memory limitation. We update over our pruning strategy to verify effectiveness of our approach. The CNN layer pruning reduces model performance significantly, while equal number of weight pruning and error is almost half with a little reduction in the model size. We also observed that 16-bit models are as good as 32-bit models. Further, we empirically study our system performance and feasibility under different realistic scenarios. Due to the square inverse law, the increased distance reduces system performance. The relative distance between subject sensor depends, as the powerful sensor can work with more distances. For example, DSLR works best with increasing distance. However, our system estimates highly accurate result from 3 to 6 feet distance for the tested edge cameras. The system performance worsen with increased relative motion between subject and sensor. Our system also can estimate PPG from angularly positioned cameras. However, the camera requires to be screen focused. The camera sensor properties plays an important role in RPPG system, as HD cameras with better lenses property is provided consistent and higher estimation accuracy. The flat camera sensors are better than wide angle sensors. We observe that USB-C cameras with HD features can capture sufficient PPG information from 3 to 6 feet. The RPPG system works best under artificial light, as the randomness of daylight variation causes system instability. To conclude, in this research work, we demonstrate RPPG system as a regular ubiquitous heart rate monitoring application system. We propose RPPG domain-specific pruning for model compression and validate using 3 datasets. Finally, we design and prototype RhythmEdge for estimation using resource constant edge devices and evaluate the system performance under different realistic scenarios. We further benchmark RhythmEdge for time, memory, and power consumption during executing RPPG component. On the top of it, we also increment RPPG data by adding more RPPG level videos under various realistic cases like videos from side views, natural light, under shadow, directional light videos. They are all open source for other researchers to use. In future, we plan to investigate RPPG improvement by parallelizing the frame by frame operations, expanding system for Android applications, incorporating edge device application, and exploring distillation based compression approaches. So Thank you everyone. If you have any question, please contact me at the following email address.